today. First, I want to thank again the sponsors, so Boltmade for giving us the room and paying the subscription. So who's part of Boltmade? Sure. Woo! And Sortable for the pizza. Sortable also provides their coding challenge.
Oh yeah, still hiring as a coding challenge.
Yeah.
Sortable, read about it.
Yeah. Yay! Okay, so what's it?
There's also shirts.
And shirts from Geek Week and other swag from Geek Week. So if you want to have a shirt from Geek Week, you can click on. Yay!
Diminishing your shirts on the class.
Yeah.
Yeah.
I'm not excited anymore.
Okay, so the talk of Stephen will be like when in a few years quantum computing will be a thing which cryptography algorithms actually will break.
Not all of them.
Yeah. Well, that was informative.
I'm sick, so I'm going to sit down. You don't have to sit down. You can stand up if you want.
Sit.
Okay. So, thanks for the enthusiasm. This is a paper that Mary found by DJ Bernstein. This is Daniel J. Bernstein.
Oh.
Yeah, better known as Qmail guy. Right? Well, he's not better known as Qmail guy. He's most known, perhaps, among like programmers for writing Qmail. Anybody know Qmail? One person knows Qmail. You know Qmail a little bit. You've heard of him.
I've heard of him.
You're not like personal friends with Qmail. Yeah. Qmail is a very security conscious replacement for SendMail, basically. It was invented or written, I think, in the late 1990s. I was kind of ignorant when it came out, but my feeling when it came out is that it was the first kind of credible. The talk around it was that it was the first really credible replacement candidate for SendMail, which had been used from the early 80s at least on almost all Unix systems, and it had a huge history of security problems and was just a mess. And Qmail was a whole ground up rethinking of everything. Anyways, yeah, that's Daniel J. Bernstein. He also wrote a DNS server, I think, and library because he got annoyed that the libraries he got from Bind were a large part of the memory usage of his Qmail processes. And he's written some other weird things too. He's an interesting person, a little bit fighty, but lots of interesting ideas. His website, his website is
Crypto.
Anyway, I don't think this paper is there. Sorry, a lot of his other stuff is there. Interesting thing. Anyway, his day job is professor of computing science at the University of Illinois, Chicago, I think. And that's what he's doing his day job when he wrote this paper. This is well, it's a chapter in a book. The book is called Post-Quantum Cryptography. It is the introduction to that book, and its title is Introduction to Post-Quantum Cryptography. See? Yeah, it all makes sense. Honestly, actually, in math, this is what they do. They just name things what they are. Like, if you have a book that's about a thing, the title of the book is just that thing. The name of that thing.
Why would they do this? Obviously, you should name your book Fuzzy Google Font.
I don't know why they did it. It's very confusing. Anyway, so let me summarize quickly the paper. It has 4 sections. These are not the titles of the sections, but these are my paraphrases of them. One is quantum computing breaks some crypto, but not all. That's sort of the thesis of the whole, not just of this section, but of the whole paper and in fact of the whole book. So he's trying, I think, to react against the hype of quantum computing as a cryptography destroying force. It's important and it changes things a lot, but it's not totally destructive. So he'll back that up. 2 examples. He gives 3 examples in detail. I'll discuss one of them, by far the easiest one. The other 2 I didn't understand very well. We'll talk about those. Section 3 is stuff that you should do before you try to use this stuff in the real world. He's got 3 things there that he thinks cryptographers and the cryptographic community should be working on: efficiency, confidence, and the usability of these systems. I'll explain in a bit more detail what he means by those 3 things. Section 4 is quantum cryptography is something else. That's not like an emphatic statement. Quantum cryptography is something else. It's, it just means that's not what he's talking about. When he says post-quantum cryptography, it doesn't mean quantum cryptography. These are different things. Post-quantum cryptography is just cryptography that will survive the transition to a world where quantum computers at scale are possible and exist. And it will still be usable and keep your secrets. Quantum cryptography is cryptography which uses quantum phenomena to do its cryptographic work. So it's like Alice and Bob can share one quantum system in the form of like two entangled photons. So Alice has a photon, Bob has a photon, and Alice measures her photon and things happen on Bob's end. Kinetic quantum method. Anyway, that's something totally different, totally unrelated to the post-quantum cryptography in the paper here. So that's section 4. We're going to return to section 4. All right, so section 1. First of all, why does it break any crypto? The main reason is Shor's algorithm. Why Shor's algorithm is the big scary thing from quantum that breaks crypto. This breaks RSA, DSA, ECDSA, a zillion other things. It's an algorithm for factoring numbers, which is exponentially faster than the fastest known classical algorithms. So a lot of cryptography is based on things being hard for your attacker but easy for you. So if you already know the factors of a number, it's very easy to factor them. If your attacker doesn't, then that's hard. So you want a significant gap in difficulty between your work, which is like encoding things and decoding things, and the attacker's work of figuring out what your secret is that you use in your code. And usually you want at least like an exponential gap between those. So if your work is polynomial and some quantity, B is normally what Dan Bernstein uses. This table here, for example, is for B bits of security. What that means is the attacker has to do 2 to the B operations to break your code. So in the simplest form, that would be the attacker, in order to break your code, has to find out what your secret key is, and maybe they have nothing better than just trying all of them, one at a time, right? So in that case, it would be like your key is B bits long, and the attacker's just going to go through them all. That's 2 to the B. That's B bits of security. The actual situation is usually not that. They're doing something more complicated, but this is a nice kind of uniform way to describe the level of security. So, right, so if you're going to have B bits of security and make the attacker do 2 to the B bits of work to break your system, it's not much good if you have to do 2 to the B work to use it. So this is the problem with Shor's algorithm, is that it creates that situation. So in the current situation with one of the classical computers, factoring is hard, exponential of some description in the size of the numbers. But if you know the secret, then things are in polynomial time, and that gap is the security. With Shor's algorithm, Shor's algorithm is exponentially faster than the classical algorithms, and it makes you and the attacker take roughly the same amount of time to do everything. So it's great if you have a secret that you really, really want to keep. You're willing to spend like the lifetime of the universe encoding your message. That's great. Then you have no problem with Shor's algorithm. But like the rest of us who are running a web server that's supposed to encrypt messages back and forth to a client, thousands of connections a second or something, you need to be able to do these things much faster than the attacker can. Yeah, Shor's algorithm, I don't fully understand it. It's not in this paper. I read a little bit about it. It's interesting. It does, yeah, the method, it's in a few steps. The first step uses number theory to change the problem from factoring n to finding the period of a sequence like this. A squared, a cubed, like this, mod n. N is the number that you're trying to factor. So you pick some A randomly, it's good enough, and you generate a sequence of powers. It has to be periodic because there are only n residues mod n, so eventually it will repeat. And then after that, you're just multiplying A, so it's by the previous number. So there's no more data for it to change its behavior on. Anyway, so it's periodic, and if you can find the period of such a sequence, then you can factor n. This gap, I won't explain that because I don't remember, and it's number theory, so there's number theory. Anyway, so Shor's algorithm is all about finding the period of such a sequence. So what you do in Shor's algorithm is you take all the powers of A, right from A to the 0 here up to A to the n minus 1, and you create a quantum object which is in a superposition of all those states. It has one possible state for every one of these numbers, and it's in a superposition of all of them. So you don't look at it yet because that'll collapse it into one of the particular states. You don't look. What you do is you apply some magical function to it that is the quantum Fourier transform, which changes a sequence into a representation of the periodicities in that sequence, which is what we care about. We want to know the period, right? So if we look at the Fourier transform of it, we'll see the spectrum. It'll have a big spike where the period is. And so once you've applied the Fourier transform, the quantum Fourier transform, you no longer have a quantum system which is in a superposition of these states, and a superposition of n states, one of which is a period, and it has a very heavy weight to being in that state. And then the problem is to look at it and collapse it with high probability into that state, and then you'll see, oh, it's in that state. That's the period. Now it's a little more complicated than that because actually, for some reason, they do it in a couple steps. First, you do the Fourier transform, and then you have a big thing, and then you look at part of it. I don't know why. So you look at this part, and then but you don't look at the rest, and then you do Fourier transform to the remaining part, and then you look at that. So there's more to it that I don't understand. So take this explanation that I gave you with a grain of salt. Okay, but this is the basic idea. The crucial fact, the thing that allows you to do much better than you can in the classical case, is that you can do things kind of massively in parallel by using the fact that the quantum state is in the superposition of a large number of things. And you magically apply functions to all of those things at once, as long as you don't look too hard. So, that's Shor's algorithm, explained by somebody who doesn't know how it works. And it breaks lots of crypto systems which are based on prime factorization and discrete logarithm. In this problem, given a and n, find the period of this sequence. That's the discrete logarithm problem. It's another one of these problems which is difficult in classical number theoretic terms. So yeah, that's why why quantum things break. Quantum computers break lots of classical cryptography. What was the name of that quantum physicist we had come here and tell us about her quantum computer? No, not you.
We had a physicist here?
Yeah.
I can't believe it.
A lady.
Yeah, I wasn't here for yours. I was here for this one.
It was last year in July.
Yes, 1 second.
You remember? It was last year in July.
Yeah, I know it was the first time that I went to the meetup.
So anyway, I asked her after she came and gave us a talk about quantum computers because she works on them. And I asked her later, what is the largest product of primes, the largest number that has been factored in real life with a real life quantum computer using Shor's algorithm? So she said 21.
Hey,
So, yeah. So if you have like a 3-bit RSA key, you should revoke it. It's not worth much anymore. Yeah, so I mean, obviously there's some engineering problems before we get a quantum computer capable enough to do this with things that we actually use in real life.
Catherine Holloway.
Catherine Holloway.
Yeah.
What's her name? Okay.
What
Yeah,
that
she
means
was-
is that it's not just like a crazy theoretical algorithm because they ran us.
Oh yeah.
So running
sure.
it anytime means
Yeah.
that like it does probably work, sort of.
Yeah, no, it does work as long as you can build a sufficiently large quantum computer to hold all the states that you want, which is the trick.
Right, the theory looks like practice.
So that's things breaking. The answer why to not all things break. There's a couple of reasons. One is that not all cryptographic algorithms rely on these particular problems, on prime factorization and discrete logarithm. So basically all the ones that don't rely on other techniques to make things hard for the attacker are still possibly viable. You have to mount a separate argument that says your quantum computer will break those. And the argument in the paper is to say basically there's no reason to think that such an argument will just appear. He says it is very striking that Shor's algorithm exists and that it breaks a bunch of things, but that doesn't mean quantum computers can do anything at all. There are systems. Let me give his list is hash-based cryptography, code-based cryptography. I don't like that one because it sounds like it's not like all of cryptography based on codes, but this is a code in the sense of error-correcting code. It's a different thing than. But anyways, lattice-based cryptography, multivariate quadratic equations cryptography, secret key cryptography, which includes AES, by the way. The last one. He says all of these. There's no reason to think that quantum computers do any better at these, or sorry, they don't do substantially better, significantly better than classical computers. Yeah, so then, of course, everybody says, well, yeah, maybe not now, but quantum computers are amazing. Somebody's going to come up with something, right? And then he says, what I think is the most interesting and mature part of the paper, is he says, yeah, but this is what we normally deal with. Right? Somebody tomorrow could come up with a classical algorithm that breaks any crypto system that you use. Right? Somebody could come up with a classical algorithm to factor numbers in polynomial time. Right? That's just a standard risk. And we mitigate it the same way that we always do, which is the cryptographic community spends time studying these things, coming up with attacks, and when you see them come up with a bunch of attacks, and then they start running out, and things don't get much better for a while, then you begin to think, okay, that's probably the best attack that anybody's going to find. Which is not like mathematical proof or anything, but it is the real world security criteria. So it's pretty good. I like that remark. So he said, he doesn't allow you to speculate about the powers of quantum computers any more than you would speculate about the powers of classical computers and mathematicians who know how to use them. So that's why there are other things which may survive. Number one. Two, examples. He does three. One of them is one of these code-based ones. It's a public key encryption system. It's based on, oddly enough, the difficulty of inverting this. Maybe we'll call this from linear algebra. A couple of naughty games. Okay, so matrix multiplied by vector gives you vector. So this will be your plain text. This will be your ciphertext that you send over the wire, and this is your secret key. And the problem is you say, you don't know how to find X from IB, and well, we all spent like half a year learning how to do that.
And so you have to introduce some error over there. Otherwise, because this is an easy problem, right?
There can be error over here, yeah. I think in this case it won't be. The secrecy will come from elsewhere. But yeah, in general you have to worry about, if I just give you B arbitrarily, it might not be in the column space at A. And then there might be error. And also, and in fact, the bigger problem with the dual to that problem is that there may be many X. And in fact, that's where the secrecy in the system comes from, is that there's many X that will do the job, and the real secret, the secret message, is hidden among this huge haystack of vectors, which could be the pre-image. So there's some cleverness with secret structure inside of A, which you can apparently exploit to make a secret public key encryption system out of using math. That's my explanation. You use math. Second example, that's his second example actually. His third is a signature system, which it's really kind of similar to this, except instead of applying a matrix to your vector, you apply a multivariate quadratic polynomial to it. So you take the elements of it as variables and you stick them all into a polynomial. You evaluate the polynomial and get a number. You do that for a bunch of different polynomials and then you send that. And again, it's a similar situation where there's some secret structure in your choice of polynomials that makes it possible for you the intended recipient to decode it. Actually, sorry, this one is a signature system, so it's just about verifying rather than the things. But the first example, which is the one I will actually explain, is the Lamport-Diffie one-time signature system. Anybody know this already? Chris Bunkhouse?
No.
No? Okay.
Is it like a one-time pad?
There's the one-time is in there, yeah, but it's, the problem with this one-time, it's a different sense of one-time. It's good, I didn't think of that, that's a good point. In one-time pad, that's kind of, maybe it is the same kind of sense, yeah. So one-time pad, it is the same reason, which is that you should only use it once.
Yeah.
You should only use your secret once. Yeah, and then it's burned, you have to
set it on fire.
Yeah, set it on fire. So let me, I'll quickly explain how this works. Your hashing system. Oh, good, I have the bottom of the board. Sit again. So your secret key has the following form. It's a bunch of bit strings, which are 2B bits long, and you have them arranged in pairs, which you label with 0 and 1. Right? And then you have a bunch of those, a bunch of pairs like this. This is a pair, this is a pair, 0 and 1, all the same length, and you have a 2B of these pairs. This is your secret key. Secret key. Okay. To get your public key, you just hash everything. Hash all the pieces individually. Hash. Use a cryptographically secure hash function, and you get, again, a bunch of pairs. pairs is saying 2B pairs, 2B bits. As before, public key. Okay, so you publicize this, you put it on your Twitter or whatever. It might not fit on your Twitter depending on your choice of B. So it goes. Right, now to sign something, what you do is you take your message. I'll simplify here a little bit. You take the message that you wish to sign. Here's the message. You apply the hash function to it. And you get, you get a bunch of bits. So you choose your hash function so that its output is 2B bits again. So it'll be 2B bits, which I'll write this way instead, 2B bits of hash. And then you use the bits of this as indexes into your secret key. So if it says, let's say 0, 1, 0, 1, 1, 0, so you take 0 here, that's this one, the first one. It says 1 here, you take, of these two, you take the second one. It says 0 here, you take, of these two, you take the first one, and so on. Okay, so you want to take half of them, and then you publish those. You publish the you don't have to do this in this version that I'm doing. So then you publish indexed halves of the secret key pairs. And that's the signature of that message. So how does this work? First of all, it's clear that you can do this. You know your secret key. You can publish these things. That's easy. To verify the signature, what a person does, they take your public key and the message and your signature. They hash the message themselves using the same hash function. It should be publicly known hash function. Okay, they get the same sequence of bits that you got. And they look at the corresponding pieces of your public key. Okay, they don't know the secret key originally, but they know the public key. And then they can verify that the secret key pieces that you publish, if hashed, correspond to the corresponding pieces of the public key. And then they think, okay, so this person who published this half of the secret key pairs, they must have known these before the public key was produced. They must have known the secret in advance, so they are the person who is responsible for that public key. Similarly, if an attacker wants to generate this signature, they have that problem that all they know is the public key and they can't reverse the hash to get the pieces of the secret key that they want. Okay? So why only release half? Why don't you just release the whole thing? And you say, look, it's me. I'm smart guys. The reason is you don't want people to be able to reuse the signatures. Okay, so an option here would be, let's say an attacker says, okay, I can't generate signatures on my own, but once a signature has been produced, I can copy it, stick it on a different message. That'll make them look like they're saying something totally different. You can't do that because that message will have a different hash. Okay? And so when people are checking the signature, they'll hash it, they'll get a different sequence of bits here, and they'll look at a different selection of the secret key things. You only have half of them from the previous signature, you don't have those same ones. And they'll check the hashes and it won't match the public key. Okay? Because you only got, in the legitimate signature that got published, only half of the secret keys were made known. Okay? Right, and this is why you can only use it once. Okay? Because the second time, right, then you publish a different half, they overlap, but you gradually get pretty close to the end of the amount of secrecy you have left gets cut in half every time you use the key. So you only use it once. Of course, we all want to sign more than one thing, so
There's an infinite number of public keys.
yes, you generate an infinite number of public keys. So what they will do is include in the message the public key for the next message. Because they'll generate a new public key. Well, the very simplistic system is you generate a new public key, secret key and public key, and you put it in the message that you're signing and say, oh, after you finish the message, you say, oh, by the way, my next message will be signed with this. And then you sign that whole thing. And then people can check that. That's awkward because it means that you have to publish all your signatures and there's a bunch of, so there's better ways to do this. Okay? Or more advanced and sophisticated versions of this scheme called Merkle trees and things, very slick. But that's basically the idea. So you say, okay, great, it's a system, I can sign things. Oh, sorry, this reminds me, Yonna gave a talk which had a very similar system for zero knowledge proofs here. There's another trick where you, for a zero knowledge version of this, where you don't have to give up secret key pieces. You can do this in like 2 steps, and you have secrets for the 2 steps, and you give either the left half or the right half of the secret. again, that you've used for the steps, and the person can't invert anything. And it's a similar issue, except that you would put a random salt in here also. Because there's a difficulty here that maybe the person making the signature is doing something sneaky with the choice of message. Maybe they generated a bunch of messages to get one which did something that they wanted. Anyway, so there's variants and advances on this. Okay, so this is a classical cryptography system called the Lamport Diffie one-time signature thing. Yeah, it's funny, it feels like somehow it's a different reason than the one-time pad, but it's not a different reason, is it? It's exactly the same signature. So, in fact, this is even more one-time than the one-time pad somehow, because the one-time pad, if you use it twice, people still have to do some work to figure it out. But if you use it a bunch of times, that you just give away all your secret keys, and people don't have to do anything. So yeah, no, this is a good, notice that. Nice. Okay, so why doesn't quantum cryptography break this? It doesn't break it. It makes it. There's all the securities in the hash function, but you can't invert the hash function. Right? So, well, maybe you can invert things with a quantum computer. Can't you do things massively in parallel? Can't you just guess all possible pre-images and then quantum computer them and then see which one is the one that you want? No, apparently you can't. There is an algorithm to do this, to invert an arbitrary function, but it's called Grover's algorithm. It only gives you a quadratic speedup. So at worst, you have to double your key lengths to accommodate that, but it's not a big deal. And any kind of hash-based security or cryptographic system will have that property, that it is resistant to quantum computers in this naive sense anyway. Okay, so that's examples. Work to do for real-world use. As I said, there's three things. Efficiency. He, of course, being a computer scientist, he speaks of efficiency in big O terms. Also in practical terms, he's better than most of that. These are all big O numbers up here that I wrote. This is an example that he gives. Elliptic curve system, I think, are based, I forget why they're secure, but they're among the ones broken by quantum computers. So these are ones which are being used in real life now. So for bits of security, you have a bunch of different things you might care about. Key size, signature size, how long it takes you to sign a thing, how long it takes you to verify a signature. These are the main operations, and if you like to be fast. And the quantum resistant, the post-quantum methods that he describes are, at this point, not quite as good. He says that he's not aware of any post-quantum method which has, I think, both B's here and a polynomial signing and verification times. So these keys and signatures get pretty big, the B cube. Like B might be, I don't know, 1,000 or something. And so you're going to end up with, like going 1,000 bits of security through your key. You're going to end up with a million-bit key and a million-bit signature. It's kind of annoying, especially if you're downloading them as part of a message from a server or something. So there's some work to be done here. That's the efficiency thing. Just find the algorithms on these principles that are faster, or find better algorithms to implement them. Two is confidence. Yeah. So again, as he says, for the problem of what if somebody comes up with something better, the mitigation there is just to throw cryptanalysts at it until they give up. Right. So we haven't done that with these methods yet. So we should do that. And three is usability. When people normally say usability, they mean oh, it has a nice UI and good features are there. He just means, can you use it? Yeah.
That is a form of usability.
Usability, yeah. I mean, it's literally able to be used, right? Usability. So as he points out, there's a lot of work in taking a mathematically sound cryptographic system and turning it into a real-world system. There's a lot of you don't just apply the mathematical function and get your encrypted message. You have to randomize it. You have to pad it. You have to build libraries that do these things securely. You have to worry about side channel attacks and all kinds of stuff. And there have been disasters using these methods of attack.
At the end of the day, your business partner is just going to tell you and say what they want to know anyway.
That is out of scope of this time. So yeah, there's a bunch of stuff to do there also. But the actual practical engineering work of turning these into real-world systems. And I think that was it.
And the quantum required, it's not quantum cryptography.
Say again?
Oh, I thought.
Oh yeah, it's something else.
It's not this thing, right?
It's not this thing.
In fact, in the way that most people in a math or computer science background understand the word cryptography. Quantum cryptography not only is something else from this, but is not cryptography at all.
Indeed. Yeah.
It, like in a Greek roots sense, it technically is, but from the way the word is used at all sense, it is not at all.
But quantum key distribution is used a lot more in the literature.
Yeah, but quantum key distribution, the crypto parts of that are just classical cryptography.
Yeah, pretty much. Like yeah.
The quantum parts are just like.
It's like having you can basically, it's like having two synchronized, it's like having two like perfectly synchronized RNGs basically. And that's what you can do.
Yeah, where someone doesn't feel like, I mean, that alone doesn't feel like cryptography, I guess.
No,
It's like,
yeah.
It's like quantum cryptography is like, it's cryptography in that you're communicating secrets and or doing some kind of signing, and so it's like, it's accomplishing the same goals,
Yeah.
but in like completely unrelated ways.
Right. It was like, what if rather than protecting against people listening in, they just physically could not?
Yeah.
And then we just talked in complaint.
Yeah, that's it. More questions?
Did you say elliptic curve is one of the ones that short algorithm does seem to break?
Yeah, elliptic curve is based on the logarithm.
Oh, the logarithm problem? Okay. Yeah, I'm not too familiar with it, so I'm not sure. I know the picture, if you draw, like draw the picture. But...
Your example.
Yes.
Your example is kind of like defensive against quantum attacks.
Yeah.
Because the secret isn't reused? Is that really it?
It is essential that the secret not be reused no matter what the attacker is doing. Because if you reuse it, then the attacker.
Quantum thing is just about the fact that the security is relying on a hash function, and there's no quantum algorithm for reversing a hash function.
But the downside is that by using a hash function, you have to keep half of your secret.
Yes.
It sounds like.
Yeah. So the one tininess of it is essential for security no matter what, even if your attacker only has a classical computer.
But there are security systems that aren't one time.
There are, yeah.
That are used.
Yes.
So I was just thinking, like even if like the classic problem, like because my understanding of quantum of this problem from the quantum perspective in depth is that if you can use the quantum computer to figure out some private key, if the private key is constantly changing, it doesn't matter. Is that not?
Oh, I see. Yeah. No. So it's not the constant changing which makes it specifically resistant to quantum computers. Yeah. So if you could use a quantum computer to find personal private keys, you would break the signature system. Yeah.
So that there's no sort of key algorithms used right now that don't rely on either discrete logarithm or factorization algorithms. That's why this one is different in that sense. And so since all of them that are publicly used right now, like RSA and whatever, would be broken, that's why I take this as an example. It's not a practical one.
Now it's interesting here because this example just says like, a cryptographically secure hash function,
right?
But like the ways that you build those are radically different. So like I assume you would need to not only verify that there's no generic way to break this in a quantum fashion, but you'd also want cryptanalysts working on verifying that like any given hash function you're specifically interested in doesn't have particular quantum weaknesses in the way that it happens to do hashing. Right?
Yeah, no, it seems like
because there's certainly not all.
Yeah, Grover's algorithm. Yeah, Grover's algorithm is very generic. So any function you give me, I'll invert it. So it's not.
But there could hypothetically be attacks developed against particular hashing functions.
Absolutely. Yeah. So that'd be worth worrying about. I don't know what the risks there are. That's a good point.
You look like a quantum dictator. That was a joke.
You will now be sent to hard labor this whole time as punishment.
I wanted to sit down so I could reenact that scene with Hitler.
Yeah, I just want to share something about real world use. So Google just started using, like on some of its Chrome browsers, experimentally they started using one of the post-quantum algorithms as an extra step, They use EC and they also used this post-quantum algorithm called LWE learning with errors,
Okay.
which is one of the algorithms that is supposedly resistant to quantum attacks.
Okay, this is why you mentioned about errors in this thing. Okay. I was not aware of these systems before this. Yeah, the one he does in the paper is the restriction is that the weight of X is known, so it's a different way of hiding X. Yeah, I don't know what errors is interesting.
Errors is basically what you mentioned, where there's this error space, and so you can't determine what exactly is the error, so you have to search through the entire error space, and that is what we expect.
To find the solution of the equation that doesn't. I see. Okay. Oh, that's nice. So it's actually practical there. Haha.
This is starting.
Yeah, just starting to use. Yeah. No, as he says, you want like decades of cryptanalytic effort against these things, so we should start now. Right, now that quantum computers are decades away. Right? This is so he wrote this book. Or God.
I guess it's decades.
Okay, that's it. Go on.